Bismillah ar-Rahman ar-Rahim. Today we are going to continue our second class in biology. And as we said before that, we are we are planning to work an integrated course to satisfy students who are running standardized tests and students who are working for GPA credits at school. Today, we are going to start with biochemistry. In this lesson, we will have an idea about some introduction to chemistry, chemistry of water. And like you see here, what's meant by pH, introduction to organic compounds, carbohydrates, lipids, proteins, and nucleic acid. These are the subtopics of biochemistry. Let's start with subtopic number 1, basic atomic structure. As you know before, the atom, what is an atom? Atom is the smallest building unit of an element that can enter chemical reaction without being divided or broken. We know, of course, that atoms can be broken in atomic plants, or like atomic bomb, atomic generators. But in normal chemical reactions, atoms are not divided. Imagine hydrogen reacting with oxygen to give water. The two molecules of hydrogen, as you know, that the molecule of hydrogen is composed of two atoms. Each molecule is diatomic molecule. Hydrogen is a diatomic molecule. Oxygen, in the same way, it is a diatomic molecule too. One molecule of oxygen is formed of two atoms. Here in the reactants, bond breaking occurs. Bonds are broken between these atoms, change molecules into separate atoms, and new bonds formation to form a chemical reaction. Here, one atom of oxygen binds with two atoms of hydrogen. As you see, number of atoms entering the reaction is this equals the number of atoms coming out of the reaction. This is number 1. The atom is not broken or changed like a billiard ball. Only bonds. The electrons outermost in shell bind together, ionic covalent, as you know. You'll see later that bond breaking needs energy and bond making generates energy. Okay? This is the atom. Hydrogen is an element. It's a pure substance made only of hydrogen. Oxygen is an element. It's a pure substance made of the same type of atoms, only oxygen. But H2O is a compound. The molecule of water is formed of hydrogen and oxygen atoms, right? Again, water is a compound. Water molecule is a compound made of more than one type of atoms, hydrogen and oxygen, bound together, either ionic, covalent, or boron. And we are going to know about bonds. This is the atom, the basic building unit of an element. that can enter chemical reaction without being divided. The atom consists of subatomic particles. The atom in general is formed of nucleus and electrons orbiting the nucleus, a positive nucleus and negative electrons. Okay, the atom has subatomic particles. The proton in the nucleus, positively charged, neutrons are neutral, and negative electrons orbiting the nucleus in certain or definite energy levels. The atom is neutral because the number of electrons negatively charged equal number of protons. The number of protons equal the number of electrons. So the atom is neutral. Everything in nature is a result of combining elements with each other. They combine with electrons in the outermost energy shell only. Okay? So all you see is a result of combination of atoms with their outermost energy shell. But the atom does not change. Okay? The electronic configuration, as you know from chemistry, has some rules. The first initial saturated at 2, then 8, then 18, then 32, and so on. But in every case, the outermost initial does not exceed 8. If you stop here, you will find some A2, 8, 8, and so on. Okay? When it reaches 8, it fills the next. It needs the next. It fills the next, then up to 8, then fills here. Anyhow, these are basic knowledge of chemistry. Okay. The atom in the elementary state always has a neutral charge, as we said, because number of protons equal number of electrons. So you will find that the number of protons gives the identity of the element. The most important number in the atom is the number of protons because it determines the number of electrons, it determines the nature of chemical reaction, it determines the identity. It is the ID number. It is the ID number, like your ID number. Example, sodium 1123. This is number of protons, 11 protons. This number, this is mass number. Mass number, it is the number of subatomic particles inside the nucleus. So you'll find here, number of neutrons equal 23 minus 11 equal 12. Number of neutrons equal 12. Nice, great. So the proton number is very, very important. Oxygen has 8. Nitrogen has 7. Oxygen is essential to life. If you breathe nitrogen only, you will die. Only one proton changes the identity of the element to a completely different thing. The proton number, because it determines the electron number, determines the chemical properties. But sometimes number of neutrons differ from versions of the same element. And we'll discuss this later in isotopes. Electronic configuration is important because it determines how a particular atom will react with another atom. Yes. As you know from your basics chemistry, if the outermost energy shell has 1, 2, or 3 electrons, it is easy to lose. If it has 5, 6, 7 electrons, it is easier to gain. So electrons either lost, gained, or shared to form compounds. So the electronic configuration determines the chemical properties. Electrons in the lowest available energy level are said to be in the ground state. What does this mean? So, for example, hydrogen. Hydrogen has only one proton and one electron in the first energy shell. Hydrogen, if excited, heated, electrons here, gets energy, it rises up to higher energy levels, rises up and become excited till it is lost to be free electron. Then comes back. If you heat a pin like this, a nail, if you heat to become red hot, what does it mean? The electrons excited move to a higher energy level, then lose energy, come to the ground state, then gain the energy, rise up in higher energy level, lose, and so on, giving electromagnetic waves in the form of red light. Sodium, heated, will give yellow light, copper, green light, and so on. So every electron is stable in its ground state. When it gets energy, it moves to a higher energy level. It's called excited. When atom absorbs energy, its electron moves to a higher energy level. The atom is then excited state. For example, during photosynthesis, chlorophyll, it is a dye. Chlorophyll and chloroplast in the plants absorb light energy, which boosts electrons to higher energy level. These excited electrons provide the energy to make sugar. How is light energy, solar energy changed into chemical energy? Subhanallah. Light energy strikes electrons or atoms in the chlorophyll to move higher, to become excited. Okay, and these excited electrons are lost. And the energy of excited electrons, the energy of excited electrons are used to form carbohydrate. What's an isotope? Look here. Carbon has 6 protons and 6 neutrons. So proton 6, neutron 6. This is called carbon 12. It is carbon because it contains 6 protons and 6 electrons. This is responsible for all chemical properties of carbon. There is another version of the same carbon, has 6 protons and 7 neutrons. 6, then the mass number will become 13. Sometimes there is another rare carbon version, 6 protons and 8 neutrons. So the mass number is 14. All of them are carbon because they have the same ID, like twins. You may have 2 twins, identical in everything, even in the fingerprints, sometimes the fingerprints. But one of them is a little fatter, have more mass than the other, fat. Okay? These are called isotopes. What are isotopes? Isotopes are atoms of the same element, having different number of neutrons or different numbers different mass number. Mass number is the number of the protons and nucleus and the neutrons. This means that it identifies the mass of the nucleus. Electrons have negligible mass, of course. So the mass of the atom is concentrated in the nucleus. Atoms of the same element, but different mass number. Right? These are isotopes. Very nice. Example, carbon 12 and carbon 14 are isotopes. Okay. Also, some other examples like iodine, okay, has many isotopes like nitrogen, like hydrogen. Many of them have. Hydrogen has 3 isotopes: protium, deuterium, tritium. These are okay, like hydrogen 1 1, hydrogen 1 2, hydrogen 1 3. Here, 1 proton, all of them have 1 proton. 1 proton, 1 proton. But here, okay? But here, 1 2 3 has no neutron, neutron equals 0. Neutron has 1 neutron, so the mass, the nucleus has 1 proton and mass neutron and 1 neutron, so the mass number is 2. Here has 2 neutrons, so the nucleus has 1 proton and 2 neutrons, so the mass number is 3. Protium, deuterium, tritium. These are the isotopes of hydrogen. Oh, it has no, it's not important in biology, important in chemistry. Other different examples, iodine 131 is radioactive. Carbon is radioactive, carbon. What's meant by radioactive isotopes? Some isotopes are radioactive. Why? Because the nucleus is crowded. Carbon, usually 6 and 6. Okay, 6 proton, but if it has 8 neutrons, it is crowded. It disintegrates. Okay, and gives radiation. How? Extra neutrons, neutron, which is neutral, changes into protons plus electron. Okay? 1 neutron changes into proton and electron. So the proton number, carbon 612, will change into another element with 7 protons. Okay? Mass number here is the same. A neutron changes into proton. The mass number is the same. 7, 14, atomic number 7, and mass number 14. This is nitrogen. Yes, look to the periodic table. This is nitrogen. Change into completely different atom, completely different element, but takes some time. If you put a piece of carbon, okay, it takes 5,000 years to lose half its weight. So it is called half-life. 5,400, something like this, called half-life. So if you find a bone, a fossil bone, find a fossil and examine it and find radioactivity of carbon here by half. So this bone has age of 5,000 years. We use radioactive iodine to diagnose and treat diseases in thyroid gland. You know thyroid gland? This is thyroid gland. You usually find this thyroid gland enlarged a little bit in pregnant women. Pregnant women find this enlarges because more activity to to work for the woman and the fetus, the baby. Radioactive isotope, radioactive carbon is used to determine the age of organic fossils. Radioactive iodine is used to treat and diagnose and help patients with thyroid gland. Uranium your radioactive uranium is used to diagnose AIDS because half-life uranium around about billion years, 1,000. Okay, and this is the basics of chemistry. Let's have an idea about bonding. Let's have a break for a few minutes to run to another topic.